Hello, Calculus and Vectors class. Here we are. This is the point where it all comes together. This is 4.6, finding derivatives with first principles. And as I kind of alluded to a little bit in the last few lessons, we're going to take the knowledge that we had from 4.1 and 4.2 about rates of change, and we're going to combine it with our new knowledge about limits, and we're going to take it and we're going to use that to build a framework for what we call calculus. So before we do that, let's do a bit of review because we haven't dealt with that rates of change stuff in a little while. So let's recall really quickly. Let's take a function like this here, and let's say we want to take the secant between 2 points. Not a great diagram, but hopefully it gives you the idea. And the secant is the line that connects two different points. And to find that slope, we're going to call those points a and f of a, and a plus h and f of a plus h, because remember we said we're interested in that interval, right? So we said it's going to be f of a plus h minus f of a all over a plus h minus a. But we said because we have an a and a minus a in the bottom, we can get rid of those and it just becomes h. So it becomes f of a plus h minus f of a over h. So that's a general formula for the slope of a secant, where h just represents the distance, the interval between those 2 points on our x-axis. So that's going to be h there. So that's our general. And to get the instantaneous rate of change, the slope of the tangent, basically, we want to get that second point as close to the first one as possible. So we want to get h as close as possible to, we want to get the second point, we want to get h as close to 0 as we can. So what we're doing is we're going to take the limit of the slopes of the secants as h approaches 0. So we're going to use that knowledge of limits, and we're going to throw that in right now. So essentially, we have this new definition for the derivative. You should recognize this. It looks almost the same as our definition for the slope of the secant, but we're going to say the limit as h approaches 0. And what that means is we're going to look at what happens to this as h gets closer and closer and closer to 0. Remember, we're looking right around h equals 0 and what's happening there. And remember, we discovered in the last couple of lessons that if we use limits, we have ways that we can work around that dividing by 0 problem that we had originally. So here's where things get really interesting, because now we are defying the rules of mathematics. We are able to work around dividing by 0. So we're going to take that definition and we're going to try and solve a problem. So basically the way this works, let's try one of these. So start with the definition. It's asking for f of x equals x squared, and we want the derivative. And what the derivative is, it's a function that's going to tell us what the slope of the tangent is at any x point. We're going to mark that with f prime of x. That little apostrophe there, that we call that prime, and that means that it's the derivative. It's telling us the slope of the tangent at a specific point x. So that's going to be the limit as h approaches 0 of, in this case, f of x plus h if f of x is equal to x squared. F of x plus h is going to be x plus h squared. So that's going to be f of x plus h. Whoops, I wrote that down completely wrong. Sorry about that. And it's going to be minus x squared all over h. Now, we still have this problem of having the h in the denominator, but we learned the last lesson that we can simplify this a little bit. We can try and see what we can do to make this a little simpler. So we already see up top that we have that x plus h squared. We know that we can FOIL that out, and we get x squared plus 2xh plus h squared minus x squared all over h. Let's collect some of those like terms. Don't forget your limit definition, and don't forget the equal sign goes just to the left of it. Now, let's take a look. We have x squared and minus x squared, so those go away. So we have 2xh plus h squared all over h. But we see that all the terms up top have an h in them. So we can actually divide out an h, and it'll help make this a little simpler. In fact, it's going to get rid of that h in the bottom. So 2xh becomes 2x plus h. So now, again, we have gotten rid of that zero in the denominator. So at this point, we're laughing. We know that all we have to do at this point is plug in whatever we said h is approaching. So in this case, h is approaching 0. So we're going to get rid of that limit definition. It's going to be 2x plus 0, or just 2x. So the final answer for this is f prime of x is equal to 2x. And what that formula tells you is, let's say if we wanted to take the parabola x squared, I'll just pick any point. Let's say if we wanted x equals 3. We can plug that into that formula, and we'd have 2 times 3, and we know the tangent for that one would have a slope of 6. So it's essentially going to tell us what the slope is of our tangent at any given point on our graph. So it's a pretty useful thing to have. It's going to give us more information about whatever curve we're talking about. Now, one more thing I want to point out really quickly is asking, what do you notice about the nature of this derivative? The thing you should hopefully notice is that f of x is quadratic, but f prime of x is linear. So I'm not going to go too much into detail about that, but let's talk about another problem. Let's see if we can find a pattern about the nature of the function versus its derivative. Let's see if we can come up with a general rule about that. So example 2 is asking about f of x equals x cubed this time. So we're going to find the derivative for x cubed. So for this one, again, let's start with our limit definition, our first principles definition for the derivative. It's going to be f prime of x is equal to the limit as h approaches 0 of, in this case, f of x plus h. If it helps, you don't have to do this if you don't want to, but if it helps, write out f of x plus h somewhere in your notes. It's going to be x plus h cubed. And what you're going to find with this is the first little big trick is just making sure you write out your f of x plus h correctly, and then it's just a matter of simplifying. So now that we have that, we can do f of x plus h is x plus h cubed minus x cubed all over h. Now that we have that, let's simplify that a bit. Okay, so let's simplify this a bit just to help us out. Let's just do x plus h, and then we're going to expand out 2 of them. So that's going to be x squared plus 2xh plus h squared minus x cubed over h. If you remember your binomial theorem from data management, that might be a little helpful here, but otherwise just keep foiling it out. Let's expand that again. Let's multiply everything by x. That's going to be x cubed plus 2x squared h plus xh. And then multiply everything by h. So x squared h plus 2x h squared plus h cubed minus x cubed all over h. Again, don't remember to keep writing your limit definition at the very start because we haven't gotten rid of that. So now let's clean this up a little bit. So the x cubed and the negative x cubed at the start and the end, they cancel. We're gonna have, let's see, we're gonna have 3x squared h. We're going to have 3 oh nope, that's going to be 3xh squared. So I realize this is supposed to be an xh squared. And then we're going to have an h cubed all over h. And again, you'll notice at this point, everything is divisible by h. So now we just take an h out of each term. So we get 3x squared plus 3xh plus h squared. So you're going to find with each of these, a big indicator of if you've done it correctly is are you able to divide out the h? Because that's the big thing that's standing in the way of us being able to find the derivative, is the fact that we have to divide by 0. So if you're able to divide by h, it means that it's a pretty good sign that you're on the right track. So last step, now that we've gotten rid of the h, we can just plug in h equals 0. It's going to be 3x squared plus 3x times 0 plus 0 squared. The second and third terms are going to just become 0, and we are left with 3x squared, or f prime of x. Now, after this one, it's asking us the same question again. What do you notice about the nature of this derivative? Let's compare the original function to the derivative. The original function is x cubed, so that's a cubic. And the derivative is 3x squared, which is quadratic. So what you're going to notice through all these, whenever we have polynomial functions, when you look at the derivative, it's just going to be 1 degree less. The derivative is 1 degree less than the original. So if we have a quartic function, we're going to have a cubic function as the derivative. If we have a degree 20 polynomial as a derivative, then we're going to get a degree 19. If we have a degree 20 function as the original function, we're going to have a degree 19 derivative. Hopefully, don't worry, I won't be that mean to show you that in this one. The math we get ridiculous. By the time we're dealing with stuff like that, we'll have some better rules to help us with this stuff. But this process is helpful because it helps us to see exactly how the rules are built, and then we can learn the shortcuts in the next few lessons. But before that, let's keep going through these, and we're going to try to keep more first principles so we can see how it works for different types of functions. So let's take a look at example 3. It's saying find the derivative of f of x equals 1 over x using first principles. Now, just to help us out, I think you guys know that we can actually write this as x to the negative 1. So it would make sense that the derivative should be something a degree negative 2. But let's see what happens as we try this. So for this one, we're going to get f prime of x. It's equal to the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. So this one is a little bit trickier to simplify. Let's take a look at the top. Probably would help if we can make this into one big fraction in the numerator. So what we're going to do is we're going to do a bit of cross multiplying, and we're going to take the first fraction and we're going to multiply the top and the bottom by x. So x plus h times x. And then the second fraction, we're going to multiply the top and the bottom by x plus h. Just so we have the same denominator. And now that we have the denominator for both as x times x plus h, we can combine those two fractions. Don't forget your limit definition. So that's going to be x minus x plus h all over x times x plus h, and then all over h. Now let's try and simplify that a little bit. Now, first thing you should notice, hopefully, since we have a fraction inside a fraction, if we're just dividing twice, really the denominators we can just put together and we multiply them together and we get x times x plus h times h. So we've just taken this bit here, this bit here. We're saying we're just dividing and dividing again. It's like saying a half divided by 3 becomes 1/6. Same basic principle. But up top, we have x minus x plus h, which becomes x minus h, or x minus x, they cancel. So that becomes minus h over x times x plus h times h. And I was a little bit messy with my terminology there, so I'm going to get rid of that equal sign, which I shouldn't have put in. That becomes the limit as h approaches 0. And now we said our big trick is, let's see if we can cancel any zeros. And in this case we can. There's an h up, cancel any h's. And we can in this case. We have an h up top and h on the bottom. So up top we're going to be left with minus 1 over x times x plus h. Now you notice we haven't gotten rid of all the h's in the bottom. But in this case, it doesn't really matter because our big objective isn't to get rid of the h's. Our big objective is to avoid dividing by 0. And in this case, if we plug in 0 for h, it becomes x plus 0, which is x. So it's not really an issue here. So in this case, we get negative 1 over x times x plus 0, which is just x. So it becomes negative 1 over x times x is x squared, which is equal to f prime of x. And take a look at that. 1 over x squared, which we know that we could rewrite as negative x to the power of 2. So we see that rule still works here. All right, we're going to do one more, and then we're going to take a pause on this, and I'll take the rest and put it into a different movie, into a different video, just to help make this into slightly more digestible chunks. Now, the next one looks a little bit different, but it's the same basic idea. The only difference here is now we have more than one term. So let's give this a try. And we said this is a quadratic, so it's probably going to be a linear function that we're dealing with at the end. So let's see what happens. So start with our limit definition. F prime of x is equal to the limit as h approaches 0 of, in this case, we need f of x plus h. That's just going to be, we're going to take each x and we're going to switch it for an x plus h. X plus h squared minus 4 times x plus h plus 5. So that's, we're going to take that, we're going to write that in for x plus h squared. Sorry, f of x plus h. X plus h squared minus 4 x plus h plus 5. And then we're going to subtract f of x, which is x squared minus 4x plus 5. And I'm going to say, put some brackets around that function. So remember that that minus carries over to everything. Otherwise, the math is not going to work out correctly. You're not going to be able to get rid of your h, and it'll still all be for nothing. So now that we have this, let's simplify a bit. We have x plus h squared. That can be rewritten as x squared plus 2xh plus h squared. Next we have minus 4 times x plus h, which is minus 4x minus 4h plus 5. And then we're just going to take that last bracket and we're going to flip the signs because we have a minus in front of it. So minus x squared plus 4x minus 5 all over h. Now that we have that, let's collect up the like terms. So let's see, we have the x squareds cancel. Let's see, we have oops, the x squareds cancel, sorry. We have, how many 2xh's do we have? We have just this one 2xh term. Let's see, h squareds, we just have the 1h squared. Let's see, the 4 minus 4x plus 4x, those cancel. We have just the 1 minus 4h term. And then we have plus 5 minus 5. So those cancel. That's all over h. And hey, would you look at that? Everything in the top of our fraction has an h with it, so we can divide out the h. So that's going to be 2x plus h minus 4. And now we just sub in that 0 for h, because that's a part of our limit definition. And we're going to say 2x plus 0 minus 4, or 2x minus 4 is equal to f prime of x. So now we have a handy-dandy equation that's going to tell us, for this parabola, x squared minus 4x plus 5, if we want to find the slope of a tangent at a specific point, now we can do that. So we can just pick our x value for our points, we plug it in, and it's going to tell us the slope of the tangent, which can be very, very useful depending on the situation. So I'm going to take a pause on this right now just because this lesson tends to be a little bit long. We'll finish this lesson off in a second video, which you'll see right after this one, hopefully. So stay tuned.